Now we move on to the inverse of a matrix. Please let's note that you can only find the inverse of a square matrix. That is why it is said here, for a given square matrix, the property A multiplied by A inverse is equal to A inverse times A, and it's equal to I, where A inverse is the inverse of matrix A, and I is an identity matrix of the same order as the original matrix A. So that means if A is a 2 by 2 matrix, I will also be a 2 by 2 matrix. If A is a 3 by 3 matrix, also I will be a 3 by 3 matrix. Note that the inverse of A will also take the same size as the original matrix. So all, in order for us to prove whether two given matrices are inverses of each other, this equation must hold. You must be able to do the left multiplication and the right multiplication, and both must give us an identity matrix of the same size. Here are some examples. Determine whether the given matrices are inverses of each other. So what you need to do, multiply A, B, get an answer, and then multiply B times A, get an answer, and check whether those two answers give us an identity matrix. Note that you have to recall how to multiply two matrices. It's a row of the first matrix multiplied by the column of the second matrix. Again, second row of the first matrix times the first column of the second matrix. Then you'll be done with the first column of your product. And then first row of the first matrix multiplied by the second column of the second matrix. Also, second row times the second column of the second matrix. That will give you the column entries of your product. Don't forget, it's always a row of the first times the column of the second. So that means if you're going to do B times A, then it means you need to write down B first and then A, so that when you multiply, you take a row of B multiplied by a column of A when you are doing B times A. Please check whether those three problems given there, those matrices are inverses of each other. Note that for number 1, you'll have an identity matrix of order 2. That means you'll have 1, 0, 0, 1. For number 2 and number 3, you'll have 1, 0, 0, 0, 1, 0, 0, 0, 1. That means an identity matrix of order 3. Now, in order for us to be able to find the determinant of a matrix, we need to be specific. Which size are we talking about? And the determinant of a matrix is going to help us to find the inverse of a matrix. Hence, while we're still under the topic of trying to find the inverses of matrices, we bring in the determinant. So let's look at the 2 by 2 matrix. It's different from finding determinants of other sizes of matrices. Now, note also the determinant of any matrix will always give you a scalar. So it means what you need to do is to find the difference of the product of the main diagonal entries minus the product of the other diagonal entries. All in all, what you're trying to do here is, if you are given A matrix A equal to A, B, C, D. AB first column, CD second column. Then the determinant of A will be A times D. That's the main diagonal minus B times C. So that means you are subtracting the other diagonal, but the main diagonal you are adding. So it's A times D, main diagonal entries, minus B times C, that is the other diagonal. That's how we find the determinant of a 2 by 2 matrix. Note, in order for us to be able to find the determinant of a 2 by 2 matrix, of a matrix, it has to be square. So it has to be a 2 by 2 matrix. If we go to third order, it has to be a 3 by 3 matrix. We cannot find determinants of matrices that are not square matrices. So the other notation for a determinant that we are able to use is the absolute value notation. If by some mistake, when you are asked to find the determinant of a matrix, you find yourself using square brackets around the entries, please write that so that we understand that you are trying to find the determinant. Note that the determinant gives you a value, but a matrix does not give you a value, which is a number. So here, if A is given by the first row, we've got 11, 4, second row, we've got 7 and 3. The determinant of this matrix, I'm hoping you are noticing that immediately the matrix itself is given in square brackets, but immediately you are trying to find the determinant, we change the square brackets to absolute value notation around all 4 entries. And then thereafter you do the multiplication, 11 times 3 minus 4 times 7, giving us the answer, which is 5. Please remember that every time you are asked to calculate the determinant of a 2 by 2 matrix, you will always get a number, a scalar. Now we quickly go to solving systems of linear equations using the inverse method. Remember that now we are moving towards being able to solve any kind of system of linear equations. But now we want to use the inverse method. In this case, there are many other methods that we're still going to learn, but for now, we are using the inverse method. So the first thing, when we're given a system, we write the system in matrix form. That's the first part. Note the first matrix represents the coefficients of your variables. Note that in the first equation, you've got A1 and B1. So it must appear as the first row of your matrix, A1, B1. And then second row coefficients of the variables A2, B2. It must appear as so. And then you've got a column vector there, which is X, Y, equal to the constants that you have on the right hand side, C1, C2. So A is equal to the matrix of coefficients, X is the matrix of variables, and C is the matrix of constants. Therefore, we're able to simply say AX is equal to C, represents the matrix form of the system of linear equations. In order for us to solve a given system, then it means we need to make X the subject of the formula. Unfortunately, we cannot just divide by A like we would do in algebra. For matrices, in order for you to get rid of a matrix, you multiply by its inverse. So all in all, in order for us to do this, it means X will be equal to A inverse multiplied by C. X equal to A inverse multiplied by C. We need to note also that I multiplied by X is equal to X. So I uses the same property as 1 in algebra. Please recall also that when we did matrix multiplication, AB is not equal to BA. So it's the same here. A inverse times C will never give you the same answer as C times A inverse. So make sure that on the right hand side, when you're solving for X, A inverse is on the left and C is on the right all the time. So all in all, we can then be able to go back to finding the inverse of a 2 by 2 matrix. Remember, in order for us to get a 2 by 2 matrix inverse, we must have the determinant first, and then use that inverse to solve any given system of equations. Now we have here the inverse given by 1 over the determinant of A. Remember that once we have the absolute value term, then it means we are solving for the determinant. And our A is A, B, C, D. But then when we're looking for the inverse, we have 1 over the determinant of A multiplied by, we interchange A and D. That's why we have got D and A. And then we change the signs of B and C. So we'll be able to have, remember, the determinant of A is just a number. So we can just multiply. Remember, when we multiply by a scalar, we multiply each entry in the matrix by that scalar. So let's do this again. In order for you to get A inverse, it means you multiply by 1 over the determinant of A matrix where you've interchanged A and D and changed the signs of B and C. Multiply out, and then you'll be able to see that you've got D divided by AD minus BC. Just remember that the determinant of A is AD minus BC. So each and every term of this matrix, which we call the adjoint of A, will be multiplied by 1 over the determinant of A. Note also that if the determinant of the given matrix is 0, then that means that matrix cannot have an inverse. Because remember that formula says 1 over the determinant of A. So if the determinant of A is equal to 0, then that means a given matrix is not invertible. So sometimes if you are asked to check whether a given matrix is invertible, the first thing you need to do, check whether the determinant is 0 or not. If the determinant is 0, then that means that given matrix is not invertible. If the determinant of that matrix is not equal to 0, then that means the given matrix is invertible. When you say invertible, that means you can invert it. You can find its inverse. So now let's determine the inverse of the given matrices. I'll try to write with my mouse here. Remember that if I'm looking for the inverse of that matrix, I'll have 1 divided by the determinant of this matrix is -6 times -2, which is 12. 12 minus 9, that gives me 3. So I have 1 over 3 into. Now I need to manipulate my matrix. The first thing that we're told to do, interchange A and D. So that means where there is -6, I put -2. Where there is -2, I put -6. And then change the signs of the other two entries. So I've got -3 and -3. So that means here, the matrix that I'll end up with, note now we've got a number 1/3, a scalar that you multiply within that matrix. So that means the first entry is -2/3. The next term is -1 and -1 and -2. Each term is multiplied by 1/3. So this is the inverse of that matrix. And the only reason why we're able to find its inverse was because its determinant, we discovered that it is not 0. So we can do the same for the next matrix. Note that I'm writing power to -1 to show that I'm doing the inverse. So we have 1 divided by, we've got -5 plus 21. -5 plus 21. That means we've got 16. Interchange those A and D values, and then change the signs of the other two. That means we've got -7 there. And then what you do, multiply out. So we've got 1/16. In place of D, you've got -7/16 in place of C. And then we've got -5/16 in place of A and 3/16 in place of B. So please check me if I'm doing the right thing or I'm giving you the correct answers. We go to C, do the same. Cos squared plus sine squared gives us 1 according to trigonometry. So we've got cos theta negative sine theta cos theta for D and positive sine theta for C. So this is our inverse. Now question 2 is asking us to use the inverse method to solve the system. Remember that we first have to find the inverse of the coefficient matrix. So let's do this. Now here, firstly, we write the given system in matrix form, and then thereafter make x, y, that is the variables, the subject. So we'll know that A inverse will multiply the constant matrix. Then find the inverse of 2, -1, 5, -3. So I've got -6 plus 5. That gives us -1 there. And then remember we interchange A and D. So interchange 2 and -3. And then change the signs of the other two. Note that we're still multiplying by 7, 18. Then we work out 1 over negative 6 plus 5, that gives us negative 1. So we can multiply out and then thereafter multiply those two matrices to get the values of x and y. As long as you know how to find the inverse of a 2 by 2 matrix, then you will be able to solve any given system of equations. So firstly, write the matrix format. Make x, y the subject, that means your variable. So that means it will be A inverse multiplied by the C. Then find A inverse. You remember that is 1 over the determinant of the original matrix multiplied by, you interchange A and D and change the sign of B and C. And then work it out, and then you multiply now your A inverse with C so that you get the final answer. Go to B, we're given another. So we do exactly the same thing, write matrix format of the given system, and then make the variables the subject. So that means we took the coefficient matrix to the right hand side and found its inverse. So let's check. It's 2 times 4, that's 8, minus 10, that gives us 1 over negative 2 as the determinant. And then you interchange 2 and 4 and then change the signs of negative 5 and negative 2. So this is what I got as the inverse of the coefficient matrix. I got negative 2, negative 1, negative 5 over 2, and negative 1. And then you multiply that by negative 14 and 11. And then thereafter you get the values for x and y. Now here are exercises where you're supposed to use the inverse method. So remember, first step, write the matrix format of the given system. Find the inverse of the coefficient matrix and then multiply that with a constant matrix, and then you'll have solved x and y. Here are some of the properties of inverses. If A and B are invertible matrices of the same size, then their product is also invertible. Okay? So if A and B have inverses and you multiply those, that means the product also has an inverse. Also note that now we use the properties of exponents. 8 to the power negative n just simply means 8 to the power minus 1 times 8 to the power minus 1 all the way n times. So that means if we got here 8 to the power minus 3, that means this is 8 to the power minus 1 times 8 to the power minus 1 times 8 to the power minus 1. You don't just raise the entries inside the matrices. You have to do the matrix multiplication 3 times. So if it's 8 to the power negative 2, it will be 8 to the power negative 1 times 8 to the power negative 1. So that means it's inverse A times inverse A. You do the matrix multiplication properly. Also, see, it says the inverse of an inverse is equal to the original matrix. Also, if we've got A inverse raised n times, it's the same as you interchange those powers. 8 to the power n, if it's possible for you to find 8 to the power n, and then you find the inverse of that, it will always give you the same answer. Same as the transpose of A inverse is the same as the inverse of A transpose. They give you exactly the same answer. Then we go to E. If you asked to find the inverse of k times a, then it's the same as 1 over k times a to the power negative 1. Remember that once you remove that bracket on the left hand side, you'll have k to the power negative 1 times a to the power negative 1, and k to the power negative 1 will always give you 1 over k. F is very important. Remember, we had said a times b is never equal to b times a. So even in this case, the inverse of the product AB is equal to B inverse A inverse. Just like we did with the transpose. The transpose of AB is B transpose A transpose. So it's the same here. So we always start with the second matrix when we do the multiplication of inverses of those matrices. Here are some examples that we could do using the properties of matrices. I'll just guide you through on what you can do. For number 1, we are asked here to determine A actually in all these three. Remember the property that says the inverse of an inverse gives you the original matrix. So all you need to do is to find the inverse of this matrix. You remember the inverse is 1 over the determinant, right, of the original matrix. Then you interchange A and B and change the signs. You interchange A and D and change the signs of B and C. Now, number 2, what you can do here is to remove this bracket. So you'll have 5. You'll have 5 to the power negative 1. A transpose inverse. That's one way you can do that. Then you take 5 and you multiply it to that matrix. And then you find the inverse of that matrix and then find the transpose. Or simply, what you could do is to use exactly the same property in number 1. The inverse of an inverse gives you the original matrix. So remember, your main aim is to find A. So what you could do is find the inverse of this. So it means just find the inverse of the matrix on the right hand side. That will be 5A transpose. To get rid of 5, you divide the matrix that you got by 5. And then you transpose it. That will give you A. It's up to you which method you choose to use. Same method that you can use even here. The inverse of an inverse gives you the original. So that means you'll have I plus 2A. Note that I has got the same order as the original matrix. So you'll have I plus 2A equal to the inverse of that matrix. And then 2A will be equal to that matrix minus I. Remember I, which is a 2 by 2, is 1, 0, 0, 1. Then when you've got that answer, you divide by 2. That will give you A. We quickly go to the Gauss-Jordan elimination. We want to use a different method to find the inverse of a matrix. So the first thing you're supposed to do in order for you to use this method, we have to formulate what we call an augmented matrix. The augmented matrix, it is the matrix between the coefficient matrix and the identity matrix. And then we perform row operations until the coefficient matrix, which is matrix A, is of the form of an identity matrix. Then the inverse will be the augmented matrix. So let's quickly go through the steps so that we get this right. First things first, remember you have written your equation in matrix form, AX equal to B. Then the next step, formulate the augmented matrix. Note on the left hand side is A on the right hand side is I. So that means this is a 2 by 2 system. So you'll have 2 rows and 4 columns, because remember the identity matrix of the same size as A also is a 2 by 2. It's 1 0 0 1. So we formulated an augmented matrix, and then what we do is to perform row operations to make sure that our A takes the form of I, and when you do whatever you do on A, it also changes I. So when you do something to one entry in a row, you have to do it to the whole row. So when you are doing the row operations, it will definitely change the identity matrix, and it will definitely change A, and you'll end up with an augmented matrix of the format I augmented to A inverse. Then A inverse is the one that you've got on the right hand side. So let's quickly do some examples and let's see whether we'll be able to do this. We're asked to solve a given system using the Gauss-Jordan elimination. Gauss-Jordan elimination allows us to use the inverse method. It means that at the end, we'll have x equal to A inverse multiplied by C. But now the Gauss-Jordan elimination comes in to find the value of our A inverse without using the determinant. First things first, write the given system in matrix form. The next step, write the augmented matrix. I'm hoping that you are following the steps. Matrix A is still here. The augmented matrix with an identity matrix is here. Now, the row operation are supposed to make sure that matrix A changes until it reaches the format of an identity matrix. So all in all, it means we need to have, where there is 2, it must be 1. Already we have a 1 there, that's okay. Where there is that 2, it must be 0. Where there is -1, it must be 0. That's what we're trying to do. So first thing I do to make sure that the first entry is 1, I divide the whole row by 2. So note the notation. I said half multiplied by row 1, and I substitute the answer in row 1. Half times row 1, substitute in row 1. So divide 2 by 2 throughout. So I've got 1, 1, and half, and a 0. Note the second row has not changed, so no changes there. I write it again as it is. All right. Now the next portion, remember the main idea is to make sure that this -1 is 0, and that +1 in the second column must be 0 as well. So first, the easiest one, 1 and -1, they give me a 0. So what I do is to add row 1 and row 2 and substitute in row 2. Note the notation. It's row 1 plus row 2, substitute in row 2. Row 1 does not change, so I rewrite it as it is. 1 minus 1 is a 0. 1 plus 1, that's a 2. Remember, I'm adding. Ne? Half plus 0 is a half, and 0 plus 1 is a 1. So now I've got this far. Now the challenge is this 2 has to change. It has to be 1. So next step, I change that 2 to 1 by dividing the whole row by 2. Hence, I've got that operation there. Half times row 2, substitute in row 2. The first row does not change, so that means the last matrix gives me the correct answers for the first row, 1, 1, half, and 0. And then in the second row, divide by 2. So we've got 0. When you divide that by 2, it becomes 1. A half divided by 2 is a quarter, and 1 divided by 2 is a half. Hence, I've got that answer there. Now, the next step, remove 1. How do I do that? All I can do is just to simply subtract those rows together. Note that I'm multiplying the negative to the row that does not change. So it's minus row 2 plus row 1. Substitute in row 1. Minus row 2 plus row 1. Substitute in row 1. And row 2 does not change. I rewrite it as it is, 0, 1, a quarter, and a half. Negative row 2 plus row 1. So I need to always remember I'm multiplying the negative to row 2. So it's minus 0 plus 1, that gives me 1. Minus 1 plus 1, that's a 0. Minus a quarter plus a half, that's a quarter. Minus a half plus 0 is minus half. Therefore, I've achieved 1, 0, 0, 1 identity matrix on the left. Therefore, A inverse is the matrix that we have there on the right hand side. Then we can be able, remember we were asked to solve the system. I know that when I've got A inverse, I multiply it to C, and then I get the values for X and Y. Let's go to the next example. Number 2, x plus 2y equal to 3, 3x plus 4y equal to 11. Same story. First things first, matrix format. The next one, augmented matrix with an identity matrix of the same size. 1, 2, 3, 4, 1, 0, 0, 1. Now, here, I already have 1 there. All I need to do is to remove 3. So I multiply the first row by negative 3 and add that to row 2 and substitute in row 2. Note that I'm substituting in row 2. Whatever I'm doing changes row 2, but not row 1. So I put 1, 2, 1, 0 as row 1. So it's minus 3 plus 3, that gives me a 0. Minus 3 times 2, it's minus 6, plus 4, that gives us negative 2. Minus 3 times 1, plus 0, that's a minus 3. Minus 3 times 0 plus 1, that's a 1. I'm hoping you're noticing that even when I'm multiplied by a negative 3 to row 1, I'm not changing row 1. I'm using the answer to change row 2. Now, the next step, I need 1 in place of negative 2. We need to always remember we're trying to get an identity matrix. So I divide row 2 by negative 2. So we've got negative half, row 2. Substitute in row 2. Row 1 still does not change. I take it as it is. Divide the second row by negative 2. So we've got 0, 1, 3 over 2, and negative half. The next step is to remove that 2. So what do? Multiply that negative, that 1 by negative 2. Hence I said minus 2 times row 2 plus row 1. Substitute in row 1. So that means the second row does not change. 0, 1, 3 over 2, negative half. And then multiply the row 2 by negative 2. So it's negative 2 times 0 plus 1. It's 1. Negative 2 plus 2, that's a 0. Negative 2 times 3 over 2, that gives me negative 3, plus 1, that gives us negative 2. Negative 2 times negative half, that gives us positive 1, plus 0, that's a 1. Hence, A inverse is that matrix. And then I have A inverse, you multiply that to C, and then you get us the answers for the values of X and Y. Now I've done this one, but I left it, some way. I need you to take it to the finish. Fill in the missing entries and give us the final answer. Here are some exercises using the Gauss-Jordan elimination to find the inverse and then thereafter solve. Note that the Gauss-Jordan also applies to 3 by 3 matrices, so I would like you to stretch it and challenge yourself by doing number 3 there. Remember, the identity matrix will be 1 0 0 0 1 0 0 0.